Part B, efficient polynomial evaluation, the topic. Okay. So you know the polynomial, and you know how to calculate, evaluate a polynomial. Yeah. But here we are talking about efficient polynomial evaluation. Okay? B.1, yeah, evaluate the polynomials. So let's look at our problem first. Yeah. Then we consider the algorithms to solve this problem. Yeah. Our computing problem number 1 for this class. Yeah. Yeah. That chessboard one, it's a simple example, so I do not count it as the computing problem we will do in this class. Okay? So this is the first computing problem in this class. Evaluate a polynomial. Data given a polynomial. Polynomial is our data. So the standard formula of this polynomial. So we write in the standard formula, and the degree of this polynomial is n. Degree. Yeah. The highest degree term, x to the nth. So the degree is n. Yeah. With coefficients, yeah. So here we assume the coefficients are real numbers. Real numbers. Yeah. So in computer science, let's assume floating point numbers. Okay? Or doubles. Yeah. The variable x can change every time. Yeah. For one polynomial, we assume the coefficients are fixed. Yeah. But the variable x can change each time we change variable x. Yeah. But if you change to a different polynomial, then you need to change the coefficients to get a different polynomial. Yeah. All right. The question, how to evaluate p of x efficiently? So here our emphasis is on efficiency. Yeah. Because I know everyone, you can find the correct answer. Well, basically what do you do? Addition and multiplications, right? And you know how to do additions, multiplications to get the correct answer. Yeah. But the question is, the way you do may not be the best way, may not be the fastest way. Your way could be very slow. Yeah. Yeah. For this class, we want to find the best solution. That means the fastest way to solve the problem. That's our main goal in this class. Yeah. All right. So here I give you the reference. Yeah. So the material I select from section 6.5 at page 234. Yeah. So here you can see, so for this material, I didn't follow the order, so I pick a later chapter topic. Yeah. The reason is, after this topic, we can do our first project. First, we do not need the knowledge from the previous chapters. No. Evaluate polynomial, everybody understands how to evaluate polynomial. Yeah. So we do not need the knowledge from other chapters. So we can jump to this topic immediately. Yeah. After that, we can work on our first programming project. Okay? Yeah. Because each project, usually we spend a lot of time. So we need to get started early as possible. Okay? Yeah. So let's study this topic first. Yeah. All right. First try, we use the method that everybody knows, the straightforward algorithm. It is an algorithm, straightforward. Yeah. All right. Yeah. But when you do the calculation, do you need to calculate each term? Then you add up all the terms, right? Yeah. 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 You need to calculate term by term, right? So then add up the results of all the terms. Yeah. Term by term, basically. Yeah. All right? So let's consider a general term. Yeah. We use this representation, a sub k, coefficient number, times a monomial, x to the kth, monomial. Okay? So we treat it as a representative of a general term. Here's the question. Can you tell me how many multiplications do we need to find the answer of this term? Just this term. We need to do multiplications. But I ask you how many multiplications. Do the counting. So, yeah. So here we need to do the counting. Yeah. The question. Here, because this k is a variable, this k can change. You do not know exact number. K is a variable. Yeah. Can you find the number of multiplications in terms of k? In terms of k. Think about that. Anyone want to try? Yeah. Number of multiplications. Okay? Yeah. Yeah. Think about that. All right. Yeah, because already it takes quite long. Now, I give you our first problem-solving strategy. Here we need to solve. This is a problem we need to solve. Okay, we treat it as a subproblem. Yeah, this is the first subproblem we need to solve in the whole big problem. Okay, our first subproblem. To solve it, no, because you didn't give me answer immediately, then I treat it as you do not feel very easy. Yeah, so you're not quite sure what is the answer. So in this situation, I want to give you an effective strategy to solve it. Yeah. All right. The strategy is very simple. Okay. The strategy. I only need to point it out. I believe everyone knows the strategy. I only need to point it out. Okay. Make you aware of it. That's enough. All right. Yeah. The strategy is do experiments. We just do experiments, okay? Yeah? If you don't know the answer, let's do experiments. Okay? When k equals 1, a1 times x to the first, how many multiplication do you need? One, right? Yeah, yeah. One, yeah. One student told me 1, okay? When k equals 2, a2 times x squared, how many multiplications? 2, yeah? Yeah, 2. X times x, one multiplication, right? Then coefficient, a2 times x squared, another multiplication, right? Okay? Yeah. Do you need to do more experiments? After these 2 experiments, can you get the answer? Is it enough? So what's the answer? Oh. What I mean, number of multiplication do here. K. K. Yeah? Because you can do induction, right? Yeah. K equals 1, it's 1. K equals 2, it's 2. If you want to try k equals 3, you can try, but you also get a 3, right? Yeah. So the answer here is k. Yeah. Yes, yes, yes. Yeah, yeah. So we call it, degree of this monomial. Okay, yeah, degree of this monomial, not degree of the whole polynomial, just this monomial. Okay, all right, yeah, all right. So this strategy. Okay, so here 2 experiments. This strategy. Yeah. So I wrote something. Yeah, but yeah, conclusion. Okay. Okay. All right. Yeah. So we did it here. Okay. All right. So here you can see it's a simple, effective strategy. Okay? Later we will use this strategy many times. So simple. Yeah. I just pointed out. Okay? Yeah. Otherwise, see, you're not aware of it, right? You need to be aware of it. Okay? All right. The next question, is this algorithm efficient? Yeah. Because in this way, we can calculate a polynomial. So the question is this straightforward algorithm efficient? Right? Yeah. Yeah. So you may ask me, what do you mean about efficiency, right? Yeah. So we need to describe the efficiency of algorithm. Yeah. Here, let me say something. So at this point, let me say something about the efficiency of algorithm. Yeah. Yeah. So we need a measure. We need a performance measure for each algorithm. Otherwise, how do you measure if an algorithm is fast or slow, right? You need some numbers, performance numbers, efficiency numbers to tell you how fast it is, right? Yeah. So regarding the performance number, there are many different ways to choose. Yeah. Yeah. Here, because if we only want to use fast, slow, that's not objective, right? Yeah? That's not objective. Okay? Fast or slow. Okay? Yeah? So we want to use number. If you use number, that's objective, right? Yeah, number objective. Okay? Yeah. All right. Yeah. So, yeah, we will discuss that objective measure later. Yeah. So here I just introduce this problem. Okay? Introduce this efficiency consideration problem. Yeah. All right. The next question, are we satisfied with the solution? No? We have a solution. The question, are we satisfied? Yeah? Yeah. So I see you feel okay. Yeah? Many of you feel okay, right? Yeah. Yeah. So let me say in this way, if you are given this problem, then I believe every one of you will write a program, implement this algorithm, right? Use a for loop, okay? Maybe another for loop, or call a math function to calculate the monomial. There is a power function, right? You can use a power function to calculate a monomial. Yeah? Yeah. So then run a for loop. You find the answer of the polynomial. Yeah. So most of you will be happy with that. Yeah. All right. Yeah. All right. Yeah. Because you do not know there is another different algorithm to solve the same problem. You do not know. This is the only algorithm you know. Okay? You do not know there is another brilliant algorithm, extremely faster than this one. You don't know. Okay? No. No. All right. So now let's explore it. Okay? So there is one, very interesting, very brilliant, interesting. All right? Yeah. But we need to explore it. Okay? Although I can give you the answer immediately, but it's not fun, right? So we want to discover it. We want to follow some logical path, logical thinking path to find the solution. Okay? All right. Yeah. So here, before we start, discover an extremely fast algorithm. So first I want to show you something. You can do the polynomial evaluation in different way. First I'll show you this. The straightforward way is not the only way you can do it. There is a different way. First of all, I want to show you this. Okay? Well, open your mind. You can find a different solution. So let me show you a simple example here. Okay? Let's consider this case, x to the k. Okay? X to the k, if you use the straightforward way, how many multiplications do you need? X to the k. We did in the previous slide, right? You use that result. How many multiplications do you need? In terms of k. Correct. K minus 1. You do not count that coefficient multiplication. In our previous case, we need to multiply the coefficient number, right? So we need one more. Here the coefficient is 1. You don't need that. So the answer is k minus 1. Very good. All right. But here, x to the 4, I just use a special example. Okay? X to the 4th. Here, I want to show you something different. So k minus 1, that's what we use our previous method. That's not the best way. Okay? Previous method. Now, let's look at the x to the 4th. If we use the previous method, the answer should be 3. But now I want to show you we can do better than 3. If you use 3 multiplication, you waste some multiplication. You don't need that many. Okay? So to calculate x to the 4th, let's do in 2 steps. The first step, x times x equals x squared. 1 multiplication. That's enough. All right? First step, 1 multiplication. Second multiplication, because we already have the x squared number, so we can use x squared number immediately, right? So let's do x squared times x squared to get x fourth. So 1 more multiplication, we get x. So in this way, we need 2 multiplications. Better than 3 multiplications, right? Here, with this simple example, I just want to show you there is a better way to calculate monomial or polynomial. There is a better way. All right? So if you try very hard, find a very smart way. Based on your understanding. If you have better understanding, you can find a better solution. All right. Next. We try to find a much better algorithm. All right, so here you can see when we do experiments, what we are doing, basically, we want to get experience, right? Before you do experiments, you do not have much experience, okay? A lot of things hidden you cannot see. After experiments, you can see something, right? You can see, you can find some properties by your observation. So here, what do we learn? We know we should have some experience. in order to get a better understanding, in order to observe useful properties, we need to do some experiments to get experience. Yeah. All right. Yeah. So now, yeah. So I want to, yeah. So before we work on the new algorithm, so here I do some preparation. Okay. Yeah. Do some setup. We need to set up for our experiments. Okay, for comparison. Yeah. All right. So to calculate a polynomial, actually we need to do two types of operations, addition and multiplication, not just one operation, right? Two different operations. Yeah. The question, how do you compare additions and multiplications? Yeah. Because people know you cannot compare apple with pear, right? Yeah. Here the same addition, multiplication, two different objects. How do you compare, right? How do you equalize two different objects? Addition, multiplication. Yeah. Here we want to use some fair way to equalize them. Okay? Use some fair way. Yeah. Otherwise, if two objects, we need to worry about two different objects, more complicated, right? Yeah. So we want to do the uniform way to deal with two different multiplications. So let's do the preparation work. Yeah. All right. Yeah. Yeah. So here, addition, multiplication. Yeah. Oh, so here. Yeah. Right. Yeah. So we apply addition, multiplication in certain order. Yeah. Yeah. We know that order. Okay. You know that order. Yeah. Yeah. So here the order is important. The order is important. Yeah. Yeah. So you can think about, is it possible if we change the order we can do better? Yeah. How do you know that's the only order you can do, right? Who told you that's the only order, right? Yeah. If you can guarantee the answer is correct, then you can use different orders to do the calculation, right? Yeah. Because only the answer matters, right? The order doesn't matter, right? The order, nobody knows. So what order do you use to evaluate a polynomial? Nobody knows that, right? Yeah. Only you know it, okay? So you only need to make sure the final answer is correct. Then you can use arbitrary order you want. Okay? Yeah. Here, we have a possibility if we change the order to do the additions, multiplications, maybe we can do better. Yeah. So here, I'll give you the, main point to work on, the order of the operations to work on. Yeah. Yeah. But how to get that order? That's so we need to do more preparation work, okay, to get that. All right. Yeah. All right. So here, about the improvement. Yeah, let me talk about that later. Improvement. Okay? All right. So here, because our goal, we want to get a faster algorithm. Faster, so the first thing we connect, that's the execution time, right? So we want a faster execution time to find the answer of a polynomial. Okay, yeah, all right. Here the question. Yeah. Here the question. Yeah. Yeah. If we use the execution time to measure the performance, algorithm performance efficiency, that's not stable. Execution time measure is not stable. Why? Because you do not mention what computer you are using, right? Do you use a supercomputer or you use an ordinary laptop, right? That's different. Do you use a, powerful server, right, with large number of processors to do parallel computing? Yeah. You do not mention the computing resource you are using, right? Yeah. So that's why we cannot compare execute time, okay? Yeah, execution time, yeah, not fair. Yeah. So that means execution time is not a good measure. It's not stable, okay? Yeah. So we want to use a better measure than that. Yeah. Yeah. So here, the hardware, yeah, because the hardware, people use different hardware, okay? Also, from the program point of view, some experienced programmers, they can implement the same algorithm in a faster way, right? Yeah. Some beginner programmers, they do not have a lot of experience, so they cannot use the fastest way to implement the same algorithm. That's also possible, right? Yeah. So from the hardware, software, execution time measure is not stable. Yeah. So we want a stable one. No matter you use any kind of hardware, any software, the measure is the same. We want that. Okay? All right. Yeah. All right. So for that one, we use this number of additions and multiplication. Number, we do the counting. How many multiplications you do, how many additions you do. That number does not rely on hardware, software, right? Yeah. Yeah. For supercomputer, you do the same number of operations. Yeah. For any implementation, yeah, basically you implement the same number of operations. Yeah. Yeah. So that's objective and stable. Yeah. Yeah. All right. So here, but here another problem: additions, multiplications. They have different execution times, right? We know multiplication is faster. Addition is faster than multiplication, right? Multiplication is much slower than addition. Okay? Yeah. So the question: how do we equalize? Yeah. They are different, but we want. In order to do comparison, we want to make our comparison fair, in a fair way. So we need to make assumption. We need to make some fair assumption in order to consider additions, multiplications together. Okay? All right, so let's do this assumption. Now, each addition takes 1 unit of time. 1 unit. Time unit. Okay? Yeah. Yeah. If we assume each addition takes 1 unit of time, then each multiplication takes 10 units of time. That's the approximate ratio, okay? 10-to-1 ratio. That's slow. You can see multiplication, one multiplication needs 10 times of one addition. That big difference, okay? Yeah. Here we make this assumption to make our discussion. Yeah. When we do discussion, yeah. Now we just consider total number of time units. Now we need to calculate total number of units of time we need for our algorithm. Yeah. We can do the comparison. Yeah. All right. B.2, estimate the cost. Yeah. Let me see how much time I have. All right, about less than 10 minutes. Okay, yeah. All right, less than 10 minutes, more than 5 minutes. Yeah. All right. Yeah. Let me just do one slide. Let's get started. Okay. Yeah. All right. Subproblem number 1. let's count the number of additions. Yeah. So here, we want to find the number of time units using our brute force algorithm. Brute force. How many time units do you need? All right, so here, the first question. How many additions do you have? Yeah, look at in this polynomial. You look at the formula. How many additions do you need to do? Can anyone give me the answer? How many additions do you need? Yeah, correct. N, yeah. Anyone say n plus 1? Yeah, around n, okay? Yeah, all right, yeah. The correct answer is n, not n plus 1, not n minus 1, okay? Yeah. But the question is, I think for most of you, you may not know how to get n, right? How to get n. Can you tell other people how to get n? No. Yes.
I mean, I just use experimentation and observation.
Oh.
If n was 1, then we would have 2 terms.
Good. Yeah. Very good. See, you can see he applies our first strategy. Okay? Do experiments. Yeah.
My instinct at first was n minus 1.
Yeah, good. Like his answer. Yeah. Good. Then you do experiments to fix your first guess, right? Yeah, that's good. That's guess and the trial strategy. We will talk about that later, okay? Guess and the trial, okay? Yeah. All right, but here I like to introduce a better way. Let me see how much time I have. 5 minutes, okay? Yeah. In this situation, actually, there is a better way to do the counting. Here we are doing the counting. Yeah. But when you count the number of additions, you know each addition corresponds to a plus sign, right? One plus sign gives you one addition. Okay? So you have another plus sign, you have another addition, right? Yeah. Then dot dot dot, you get lost. Okay? Yeah. So when you see a plus sign, you know you have an addition. But we may have a large number of terms. You cannot list all the terms, right? You have to use the abbreviation in your formula with dot dot dot. Then you get lost. We cannot keep track of all the plus signs, right? How do you keep track of all the plus signs, right? Here, I introduce an effective way to keep track of all the plus signs. When we get lost, okay, we want to find some fixed milestones to help us locate those plus signs, how to keep track of, okay? Milestones or reference points, okay? Reference points to help us keep track of those plus signs. Okay. Let me show you the concrete way to do it. Can we associate the first plus sign to the first subscript? 1, A1. A1, that one subscript. I associate the first plus sign to the first A subscript. Yeah. Skip the A0, okay? We skip A0, okay? A1, the subscript of A1, okay? Can we associate the second plus sign to the A2 term? A2 term, the subscript. Can we associate next plus sign to next subscript and so on? Okay? The last plus sign we associate to the last subscript. In this way, you do the 1-to-1 correspondence, right? One plus sign corresponds to one subscript. 1-to-1 correspondence. The subscripts you have 1, 2, 3 consecutive integers from 1 to n. Is it easy to keep track of these subscripts? n consecutive integers. So when you do the counting on these n subscripts, your answer is n. Okay? But when you count the number plus sign directly, you may get lost. Right? So this method, I call it counting by reference. You only need to find the reference objects, appropriate reference objects. If you can identify appropriate reference objects, and you can establish one-to-one correspondence, then you can do the counting easily. Okay? Yeah. All right. So let me stop right here. Yeah. Next time when we start, let me summarize this counting by reference method. Summarize it. Okay? So then we solve the remaining of the problem. Yeah. All right. That's it.